Hello and welcome to this lecture on analytical chemistry. Specifically, we'll be talking about mass spectroscopy. So we'll be taking a journey through multiple topics on mass spectroscopy, from its background, from its theory. We'll be looking at some instrumental components. We'll be looking at how we can analyze some chromatograms, and we'll be just having a look at how we can use mass spectroscopy in analytical chemistry. So mass spectrometry measures the atomic or molecular weight of an ion from the separation based on its mass to charge ratio, which is the m over z. So this helps us to look at the elemental composition of matter, the structures of inorganic, organic, and biological molecules, because eventually we'll see that what we'll measure will include what are called fragments of the molecule. So these are just different groups of atoms from a particular molecule. And so if we piece those together, it can help us to understand the structures of unknown molecules. Qualitative, quantitative composition of complex mixtures, isotopic ratios of atoms in the sample, and it is one of the most routinely used analytical techniques. So you can see here a little bit of a what we would call a timeline of the history of mass spectrometry up to, I suppose, the most recent Nobel Prize in this area, just done as a chromatogram. So here are, well, 5 winners of Nobel Prizes for their work on mass spectrometry. So the first was back in 1906 by Joseph John Thomson for the first mass spectrometer, and right up until 2002, where it was shared amongst a couple of different scientists who developed different mass spectrometry techniques. So mass spectrometry can give us a wealth of information. It can be used for qualitative and quantitative analysis. So we can see here down the bottom a chromatogram for a particular sample. And we can see that we'll have a number of different peaks with relation to their mass to charge ratio, and then, of course, the relative abundance. So some examples of use of mass spectrometry. So we can have qualitative analysis. So it'll be molecular weight determination and structure determination. We can have quantitative analysis. So it can be used in different things like biotechnology, pharmaceutical, clinical, environmental. Maybe you're looking at water, food, or air quality tests, geological, toxicological, and forensics. So we've probably already encountered atomic spectroscopy. So how does it differ from mass spectroscopy? So there are a number of advantages and disadvantages of mass spectroscopy over atomic spectroscopy. So some advantages over atomic optical spectroscopy are the detection limits are 3 orders of magnitude better in mass spectroscopy, a remarkably simple spectra that are unique and easily interpreted, and ability to measure isotopic ratios. So we can see a little bit of the comparison of spectra for optical ICP analysis and ICP-MS. So this might be ICP-OES or something like that. We can see the peaks are not very well resolved over the wavelength range measured. They are quite sharp, but the resolution here is not great, and it would probably be difficult to use this for any sort of quantitative measurement. Whereas we can see here at the bottom, we have an ICP-MS spectrum, and so this has much nicer resolution amongst many of the peaks, and it would enable us to use this both qualitatively and quantitatively. There are, of course, some disadvantages. It's very typically the spectrometers are very expensive, at least compared to atomic spectrometers. Instrument drift that can be as high as 5 to 10% per hour, and interference effect. So we need to recalibrate quite regularly. And there are a number of interference effects which you don't typically see in atomic spectroscopy. So atomic weights in mass spectroscopy. So of course, you need to know a little bit of background. So ultimately what we're doing is we're discriminating amongst the masses of isotopes. So you will get peaks based on the different isotopes of atoms in a particular molecule. And we can't just take the average mass as we often do when we're calculating, for example, molecular mass. We have to use and understand the individual masses of the isotopes of a particular element. So this is quite different from many other analytical techniques where we simply use the average atomic masses. So of course, a little bit of background on atomic masses is given here. And then of course, we're using the exact mass instead of what would be the average mass. Atomic weights in mass spectroscopy. So we have chemical atomic weight or average atomic weight would be given like this, where we would have it made up of the different atoms and their fractional abundance of each isotope, and then n being the number of isotopes here. So the weight of interest for most purposes, the sum of chemical atomic weights for the atoms in the compound formula. So for example, if we have methane, then the exact weight would be this. So it would be 12.01115. So that would be the most abundant form of carbon times 4 times this mass for hydrogen would give us 16.0434 Daltons as the weight of the exact weight of our methane. So typical atomic masses in the periodic table are found. So like, for example, we can see here below a mass versus charge spectra for boron on the left and zirconium on the right. So for boron, we can see that if boron 11 is 100% abundant, and then, so that's relative abundance. So in terms of relative abundance, we simply place the largest peak as being 100, and then all other peaks are going to be some fraction of that. So the boron 10 peak is 23% of the boron 11 peak. And so if we then determine the mass of boron from that, we can find out here that is 23 times 10 plus 100 times 11 gives us over 123. The sum of the two abundances will give us a mass of boron as 10.81. So that's typically what we use and find in the periodic table as our masses. But here are the relative abundance of natural isotopes. You don't need to necessarily learn this, but this is for reference anyway. We can see different elements here. For example, we have beryllium, beryllium 9, pretty much totally 100% abundant. Hydrogen has 2 isotopes, mostly hydrogen 1, some hydrogen 2. Very little tritium actually exists naturally. And you can see for different elements throughout the periodic table. So molecular formulas then from exact molecular weights. So this requires identification of the molecular ion peak. And so exact mass needs to be determined. So this means that we need high resolution instruments because as we've seen, there can be quite a small difference in the actual weights. So we need to detect mass differences of a few thousand atomic mass units. So purine, we need to be able to separate these basically, and they all have very similar weights. And so how we would do that is by looking at the relative abundances of the different isotopes. So the molecular ion peak is 120.070 plus or minus 0.005. So only C7H8N2 is a possible formula in that range. So this here, benzamidine. So the precision of a few parts per million is routinely possible. So we could actually differentiate between these 4, assuming that we have a significantly high resolution instrument. So low resolution instruments are only able to differentiate whole number masses, and this requires sufficiently intense molecular ion peaks. And so it requires accurate heights for the M+1 and M+2 peak, because those will ultimately give us sort of like an indication of what kind of isotopes might be present. And so here's a calculation maybe of some of the peaks that might be present or the masses that might be present for the different M+1 and M+2 peaks. So for example, if we looked at the other isotopes of carbon, hydrogen, nitrogen, and oxygen in this molecule, or for this molecule, then we could determine the ratio of the M+1 peak over the M+ peak as being 7.44%. So I mean, like if we had 100% for this peak, then we would expect to see a 7.44% peak for the M+1. So resolution in mass spectroscopy is as important as it is in other forms of analytical spectroscopy. So we need to be able to differentiate between the masses in order to be able to tell how much of something we actually have. So the resolution here is given as m over delta m, or r, the resolution is equal to m1 plus m2, so the two peak positions divided by 2, so the average of the positions divided by delta m, the difference in the two masses. And so the higher the number for R, the better the resolution. So for example, 500,000 is better than 500. A resolution of 4,000 would resolve peaks occurring at mass charge ratio values of 400.0 and 400.1, or 40.00 and 40.01. And so this is just an example of some of the resolutions that might be required. So if we like zoom into this peak, we can see that there are some overlapping peaks here, which are not typically very well resolved. And here's an example of maybe some of the things that we need to know in determining the resolution. So how would we then do a calculation on the resolution in mass spectroscopy? So we want to calculate the resolution to differentiate two mass peaks. So A, it's C2H4 plus with given this mass, and CH2N plus given this mass. And then the second part, B, is this. So I'm only going to do part A, and then part B, you should try yourself. So part A, since we're not given any additional information, we have to assume that the peak heights are the same, which means that we're going to use the second formula on the previous page. We're going to use this formula here. We can't use this one because this one relies on, well, first of all, we have the peak position of the second peak m, but we don't have the half width or the width at half maximum of the first peak. So we can't use that. So we have to use the second equation. So it's okay. So we've got the second equation here. And then we fill in the values from the question. So we've got the C2H4 peak position. We've got the CH2N plus peak position here. Again, assuming that these are in fact the same height and that they're relatively identical peaks. Then divide that by 2, and then we get the difference in the masses here. It's important also to make sure that we report. I mean, in this case, it's kind of obvious because it's in the question, but if otherwise we were looking at this just to report data, we should always make sure that we report the position that this data was taken at, which mass charge ratio, so around about 28.0. So then we find out that R is around about 2,224, a little bit more than that, but around about that value. So the resolution is okay there. It's not great, but it should be enough to resolve these peaks. And so that's how you would calculate the resolution, given that information. Given no other information, we don't know if we don't know very much about the peaks at all, except their positions. So we have to assume that they are indeed going to be the same height and same width, more or less identical. So identification of odd electron ions, this is the nitrogen rule. So this is based on an anomaly in the relationship between the atomic weights and the valences of the common elements. An organic molecule containing the elements CHOSP or a halogen are often going to be included in this. So odd nominal mass if it contains an odd number of nitrogen atoms, even nominal mass if it contains an even number of nitrogen atoms, including 0. So even nominal mass gives an even valence. An odd nominal mass will give an odd valence. So here we're looking at the number of nitrogen atoms that are contained. So we have one nitrogen atom here, which is an odd number, which means that we should have an odd nominal mass, and we do. Here we have N2, so we have an even number of nitrogens, so we should have an even nominal mass. The last one again is 1, so that's odd, so that gives us an odd nominal mass. Here we also have 0 nitrogens, which according to our rule, the nitrogen rule, we will have an even nominal mass. Indeed, that's true. Nitrogen is the exception to itself. So double bond equivalence then, so the number of rings or double bonds that an ion contains is going to have to be accounted for. So this is calculated from the elemental formula as follows. They're given the equation there, where D is the unsaturation factor, I max is the total number of different elements, Ni is the number of atoms of an element I, and Vi is the valence of atom I. So here we see the mass spectrum for hexane and hexene, and that's going to, the large differences between these is going to be largely due to the presence of this double bond. So mass spectrometers, how do they appear? What do we have? So atomic mass spectrometry involves the following steps. So this involves atomization, conversion of atoms to ions. Most ions then are going to have a single charge, separation of ions based on the mass to charge ratio, MZ, and then the counting the number of ions of each type, or measuring the ion current. Principal components then of mass spectrometer are going to be the vacuum system. So this is going to be needed to maintain the low pressures required. We're going to obviously have an inlet because this is where we're going to get the micro amounts of the sample into the ion source. And then the ion source is where we're going to convert it into a gaseous ion by bombardment with some form of energy, whether it be electrons, photons, ions, molecules, or thermoelectric energy. The positive, negative ions then are accelerated into the mass analyzer. The mass analyzer then disperses the ions, and the transducer, of course, then converts the beam of ions to an electrical signal. Because ultimately, in most of analytical chemistry, what we're actually measuring is not, in fact, how much of our sample is present, but rather some sort of an electrical signal. So types of atomic and molecular mass spectroscopy. So we have thermal ionization and spark source. So this is the first type of mass spectrometry. And then we've inductively coupled plasma ICP. So this is the current common approach, because as we saw in atomic spectroscopy, ICP produces a very high flame temperature, which is very stable and very good at atomizing samples. So here's just a summary of the different types. So we've got ICP-MS, so that's using different atomic ion sources. So this is using high temperature argon plasma. And the typical mass analyzer is quadrupoles, which are the sort of common modern standard. And then we have different types here. Then ion sources for molecular mass spectroscopy. So if we are doing it in the gas phase, then we have electron impact or chemical ionization. And then the ionization agent is the energetic electrons or the reagent gaseous ions. So mass spectroscopy theory. So mass analyzers use electric and magnetic fields to apply a force on the charged particles. So this is going to be related with Newton's second law, force is equal to mass times acceleration. And it's also related with Lorenz's force law, where F is equal to the ionic charge, E times the sum of this term, or this set of terms inside of the brackets, where E is the electric field strength plus V times B, which is the vector cross product of the ion velocity and the applied magnetic field. So the ion velocity V and the applied magnetic field here. So this is the vector cross product. So the force is therefore dependent on both mass and charge, and spectrometers separate ions according to the mass-charge ratio, MZ, and not by mass alone. So inlet system, so how do we actually get the sample into our spectrometer? So we introduce the sample into the ion source with minimum loss of vacuum. The spectrometer is equipped with multiple inlets for different sample types. So depending on what basically we're looking at. So we've got a batch inlet, we've got direct probe inlets, we've got gas chromatographies, liquid chromatographies. So these are good for analyzing complex samples. So you can first of all separate your sample into different components and then measure them each individually. So here's just a look at a typical mass spectrometer setup. So this looks like an ICP-MS. So we inject our sample here, we spray it through the nozzle, and then it's passed through a carrier gas here. We generate the aerosol, it passes through the ionization through the ICP part. So here it is ionized, and then the particles that come out of the flame pass into the mass spectrometer here, and then through the quadrupole selectors, and eventually we get our data out at the end. So let's have a look at each one of these in detail a little bit. So external batch inlet systems, these are the simplest. They're good for gas and liquid samples where boiling points are going to be less than 500 degrees Celsius. The sample is then typically heated to some temperature below 400 degrees Celsius in a small external oven. The sample pressure then is around 10 to the minus 4, 10 to the minus 5 torr. vapor admitted to the ionizer through the valve, and then the gas steam added to the analyte. So we have the gas introduction. We have a metering volume place, just to make sure that there is a consistent volume of gas flowing through. Then we have the liquid introduction. Then they mix. Here they're heated. This way goes to the vacuum. Continuously heated through here. They pass through a pinhole to the ion source where they'll be ionized. Here is a direct probe inlet for solids. So the direct probe is very small. And so the probe moves through various lock system stages and permits for a stepwise increase in the vacuum. So the direct probe is for solids and non-volatile samples. So less sample is required and wasted. So a few nanograms is all that is required. The sample is held in the surface of glass or an aluminium capillary tube, fine wire, or small cup. And the sample vial is inserted through the airlock and into the ionizer chamber. The lock system minimizes the amount of air that must be pumped from the system, and the vial is then heated to vaporize the sample. The vial can be reduced to a capillary or surface plate for small quantities. So these are some other inlet systems. So we have here, for example, this is the sample being mixed with argon gas, and then creating an aerosol. So liquid chromatography and gas chromatography coupled to a mass spectrometer. So this is just an example of the chromatography process. So you can see the separation of peaks A and B, and then that will give us different detections. So here we'll see for detection A, substance A spectrum, and substance B spectrum, and we can have those separate. So this permits separation and determination of components for complex mixtures. It requires a specialized inlet system, of course. The major interference problem here is the carrier gas dilution. The jet separator separates the analyte from the carrier gas, and the lighter gas, carrier gas, is deflected by the volume, and the heavier sample travels in a straight line. So here, this is basically what is happening. So we have sample passing through, coming out of the gas chromatography, where it's been mixed with some sort of carrier gas, oftentimes helium. That helium is very light, much lighter usually than our sample. So the sample will pass through this and will mostly travel in a straight line. Now, there will be some mass losses into the inlet for the mass spectroscopy ion source. And so, but the advantage here is that even though we lose some of the sample, we lose almost all of the carrier gas because of its lightness. It is deflected by the volume. Basically, it wants to fill the volume more than it wants to travel in a straight line. And so as a result of that, most of it passes into the vacuum chamber and is pumped out. But then the sample, some of it is lost, that's true. But most of it will pass through and into the mass spectrometer. So ion sources, the formation of gaseous analyte ions happens. So the mass spectrometric methods are dictated by ionization techniques. So the appearance of the spectrum is highly dependent on the ionization technique. So for gas phase, we have a sample is first vaporized, then ionized, and the thermally stable compounds used for thermally stable compounds, boiling points of less than 500 degrees Celsius, and the molecular weight is typically quite small. Desorption processes then are for solids or liquids directly converted to gaseous ions. And so this is for things that can have quite large molecular weights. So maybe a biological system. And so here's the difference. So depending on the phase or the characteristics of the sample, we can use different types, gas phase or desorption phases. And then of course that then changes the different types that are possible. And then of course the ionization process is different for each one of these as well. So ion sources, so this is how do we ionize? So we've got different sources. We've got hard sources and soft sources. First, we'll look at hard sources. So they need to have sufficient energy so the analyte can be in a highly excited energy state. The relaxation then involves the rupturing of the bonds. So this produces fragments with the M-Z ratio, which is going to be less than that of molecular ion. Well, it means a fragment of the molecular ion, so it should be less. And so the kinds of functional groups then will give us structural information. So if we know a little bit about it, what we have in the molecule, then it will serve us well because we'll be able to hopefully assign the different peaks to their mass fragments. Soft sources then cause little fragmentation. So the mass spectrum consists of the molecular ion and only few, if any, other peaks. And so this will give us a nice accurate mass for our molecular ion. Electron impact sources, so these are EI. So the sample is heated to produce a molecular vapor, and then it is bombarded with a beam of electrons. The electrons emitted from the heated tungsten or rhenium filament. Electrons are accelerated by a potential of 70 volts, and the path of electrons and molecular ion at right angles. We form positive ions, and then the electron beam expels the electron due to the electrostatic repulsion. So M plus an electron goes to M, goes to an excited form of the molecular ion plus 2 electrons. It's not very efficient. 1 molecule in a million is ionized. The positive ions are attracted to the first slit by a small potential of 5 volts, and then the high potential is applied at accelerator plates to accelerate it through, and this generates the molecular ion velocity that we will need. Electron impact source, so this hard source 50 volts higher than that of chemical bond. The highly excited vibrational rotational state. Electron beam does not increase translational energy, and relaxation results in extensive fragmentation. So we have a large number of positive ions of various masses, typically less mass than the molecular ions. So lower mass ions are called daughter ions. So these are the ones that are less mass than the molecular ion. And sometimes the molecular ion is not even present. So here are some typical reactions in an electron impact source. So we've got a molecular ion formation and then fragmentation. So we form the molecular ion and then we fragment it through relaxation processes, and then these can even relax further into different fragments. We can even have rearrangement followed by fragmentation. So this energy can cause a rearrangement in the molecule, especially if it has different conformers, and then the collision followed by fragmentation. Electron impact source. So the base peak is the most intense peak, usually a daughter ion or fragment ion. Peaks at molecular weights greater than the molecular ion. So the same chemical formula, but maybe different isotope composition. So remember that some isotopes can be larger than the most abundant. And the size of the peak will depend on the relative natural abundance of isotopes. So the collision product peak, the M+1 plus peak, is from collision transfers of a hydrogen atom to the ion to generate a protonated molecule. Second order reaction here, so this depends on the concentration and increases with increase in pressure. So this is the result of protonation of our molecule. So it's not possible for it to protonate, then this M+1 ion is probably not going to be present. So advantages of an electron impact source, and it's got good sensitivity, and the fragmentation generally provides unambiguous identification of the analytes. However, there are some disadvantages, so there's a need to volatilize the sample, so thermal decomposition before ionization happens, and then fragmentation, so there's a disappearance of a molecular ion peak, and so the molecular weight is not yet determined. Then the next ion source, chemical ionization source, CI. So electron impact and chemical ionization are interchangeable in a spectrometer. Chemical ionization is the second most common procedure for generating ions, and gaseous atoms from the sample are heated for a probe, collide with ions produced by the reagent gas bombarded by electrons, and this is usually positive. Usually we have positive ions. So we need to modify the electron beam. So we add a vacuum pump capacity. We reduce the width of the slit for the mass analyzer to allow a reagent pressure of 1 torr in the ionization error. And we want to keep the pressure below 10 to the minus 5 torr in the analyzer. So the concentration ratio of the reagent to sample is 10 to the 3 to 10 to the 4, and the electron beam preferentially interacts with the reagent sample instead. So chemical ionization sources, additional, so we have soft sources. So methane is a common reagent. We can also use propane, isobutane, and ammonia. So this reacts with high energy electron beam to generate several ions. And these can react with other methane molecules to produce different fragments. So the collisions between the sample molecule and CH5 plus and C2H5 are highly reactive, and they involve proton or hydride transfer. So if we've got a proton transfer, then typically we'll have an M+1 plus peak. If we have hydride transfer, then we'll have an M-1 plus peak. And then a C2H5 plus transfer is going to be the mass plus 29 plus. So basically we're adding this onto another molecule. That is possible. So MALDI, this is the one that was a share of the 2002 Nobel Prize. So this is accurate molecular weight for polar biopolymers. So this such as DNA, RNA, proteins. So this is a few thousands to several 100,000 Daltons are possible. The sample is mixed with a large excess of radiation absorbing matrix material. So here are matrices that are commonly used for MALDI together with their usable wavelengths shown here. So the solution is evaporated onto a solid surface. Then the sample is exposed to the pulsed laser beam. So this causes a sublimation of the analyte ions, and the MS spectra is recorded between laser beam pulses. So here's an example of how MALDI works. So typically some of the advantages are that it has low background noise. So at high molecular weight, the matrix causes significant background at low molecular weight. So it's not really suitable for small molecules, but it's very suitable for large biomolecules. So there's typically an absence of fragmentation. So we have multiple charged ions, however, maybe +2, +3 instead of just +1. It's also possible to observe dimers and trimers. The mechanism of MALDI is not completely understood. The matrix compound must absorb the laser radiation and be soluble enough in the sample solvent to be present in large excess, and the analyte should not absorb the laser radiation. Otherwise, fragmentation will occur. So basically, the laser produces a lot of energy at specific wavelengths. However, if those wavelengths are also going to be absorbed by our large molecule, then we will get fragmentation because the energy will be used during the relaxation process to fragment the sample. So here's an example. So we've got a laser beam coming in onto the surface, and it is going to desorb the matrix and analyte ions. The matrix should hopefully absorb the laser radiation where the analyte does not. And then they will pass through an extraction grid and into the time of flight mass analyzer. And here's a simulation of the MALDI process. So we have the beam coming in. So we've mostly got matrix and cations, and then some analyte molecules, these green spheres. So because of the laser, then they are going to be desorbed from the sample plate. So the MALDI spectra are greatly influenced by the type of matrix solvent and additive. At high molecular weight, the matrix causes significant background at low molecular weights. So you can see here a couple of different time of flight MS spectra of yeast ribosoluble proteins over here on the right, and then we can see here on the left. On the right, then we can see the effect of the different matrices on the same sort of mass charge ratio area. You can see that some produce more fragments than others. So electrospray ionization, so ESI, is one of the most important techniques for analyzing biomolecules. So we have polypeptides, proteins, and oligonucleotides. So these inorganic species, or other types of samples which can be analyzed, are inorganic species such as synthetic polymers. So typically we're looking at molecular weights in excess of 100,000 Daltons. So it uses atmospheric pressure and temperature. The sample is pumped through a stainless steel capillary at a rate of a few microliters per minute, and the needle at several kilovolts is potential is applied. And this creates a charged spray of fine droplets. And so you can see here a schematic of the plasma process. So the aerosol is dried, particles are decomposed and dissociated, atoms are then formed and ionized, and then eventually the sample cone and the analytes are present as the M+ ions. So during ESI, they pass through the desolvating capillary. So this causes the evaporation of the solvent. So we typically just then have the analyte present. And then we have the attachment of charge to the analyte molecule. So this produces our ions, which are important for our analyzers. And then the molecules become smaller, and so we have a charge density becomes greater. So we've got desorption of ions into the ambient gas. Then we get little fragmentation, which is good for thermally fragile biomolecules. Ions can sometimes be multiply charged, however, so the MZ values are small. We have detectable, but it's still detectable with quadrupole setup. And then the average charge state increases more or less linearly with molecular weight. Then we have fast atom bombardment sources, FAB. So the major role for MS studies of polar high molecular weight species. So this is soft ionization technique. So it's good for molecular weights greater than 10,000 and structural weight or structural information for molecular weights of around 3,000. The samples are in the condensed state, so glycerol solution matrix, and the liquid matrix helps reduce the lattice energy. So they're ionized by bombardment with the energetic xenon or argon atoms to a very rapid sample heating, which reduces the sample fragmentation. And we have positive and negative analyte ions are sputtered from the surface during a desorption process. So this must overcome the lattice energy to desorb an ion and condense a phase. So the healing, the damage induced by bombardment. So you can see here the sample matrix is bombarded with these high energy cesium atoms or ions, and then this produces what we need for our analyzing of the masses. So during FAB, there's a beam of fast energetic atoms which are generated by passing an accelerated argon or xenon ions from an ion source through a chamber. The chamber contains argon or xenon atoms at 10 to the minus 5 torr, and high velocity ions undergo a resonant electron exchange reaction without substantial loss of translational energy. So there's going to be a production of fast atoms. So this accelerated argon ion from the ion gun. We have a ground state argon atom, and then we have charge transfer to a slow ion and a fast ion, or fast atom, sorry. Okay, so let's have a look at a spectrum. How would we determine the ions responsible for the peaks, and what are they going to be their mass spectra? So we'll do one half, which was the 117, 119, 121 half, and then the other half I'll let you do for yourself, this half. So our molecule is 1112 tetrachloroethane. So we've got 3 chlorines on one carbon and 1 chlorine on the other carbon and 2 hydrogens attached here. And so we want to know what this is. So the first thing that typically you can do is to take the mass, the peak of this area, and then we're going to subtract that from the molecular weight to see what's been removed. So 167.85 minus 117 is equal to 50.85. So how would we get to that? So it would be typically 37 chlorine plus CH2, which would be 37 plus 14 would give us 51, remarkably close. So the peak at 117 is going to be most, so that would correspond to this half of the molecule. So that would mean what we are left with is this part. And so that means we have the mass peak at 117 is most likely CCl3 plus, which is that part there. Okay, so how do we analyze the masses? Using mass analyzers. So we've got double focusing analyzers, so 2 devices for focusing an ion beam. So we've got an electrostatic analyzer, which is here, and we have a magnetic sector analyzer, which is here. So the ions are accelerated through the slit into the curved electrostatic field. This focuses the beam of ions with the narrow band of kinetic energies into the slit, and then the ions enter the curved magnetic field. Lighter ions are deflected more than heavier ions. And then obviously we can get an ion collector. We can then, of course, transduce that and eventually get a nice spectrum. So inside the double focusing analyzer, we have a curved magnetic field of 180, 90, or 60 degrees. So we can vary the magnetic field strength or accelerating potential to select for ions of different mass. Kinetic energy of accelerated ions before the magnetic field. So kinetic energy is equal to the ion charge, theta, times E, the electronic charge, times V, the ion velocity, which is also equal to, the voltage, which is equal to a half of the mass times the ion velocity squared. So the path through the magnet depends on the balance of 2 forces, the magnetic force and the centripetal force, where B is the magnetic field strength and zeta, E, and nu are the same as up here. So it's velocity, electronic charge, ion charge, and B is the magnetic field strength. And then FC is the centripetal force. This is going to be the mass times the velocity squared over R, which is the radius of the curvature of the magnetic sector. Then, of course, Fm is equal to Fc, so we can substitute these 2 equations into each other, and we can get a value or a new equation expression for velocity. And then if we substitute the velocity into the kinetic energy equation up here, we get a new form of the equations here. And so we can select masses by varying the current in the magnet. So we can see here M over Z. So this is mass over charge. That's what we measure in a mass spectrometer. And we can see that R is not really going to change. E never changes, and V is not going to change. Well, V we can change. But generally we keep these three are all going to be the same. And then B, by changing the current of the magnet, we can select different masses. So double focusing analyzers, that's a different kind. So this is just a schematic of that. So it's just a different schematic. Still got the same components as before. Quadrupole mass analyzers then, so these are quite common now, so they're more compact, less expensive, and quite rugged. So they have a high scan rate, which gives us a spectrum in around about 100 milliseconds. So what we have here are 4 cylindrical rods that serve as electrodes. So we have one pair attached to the positive side of a variable DC source, which are typically opposite each other, and the other is going to be on the negative side of a variable DC source. So the variable radio frequency AC potential, which is 100 degrees out of phase, is applied to each pair of rods. So the ions accelerated through the space between the rods where there's a potential of 5 to 10 volts. The AC and DC voltages are increased simultaneously, with the ratio being constant, and all ions without specific mass charge strike rods, ions without specific MZ strike the rods and become neutral, and only ions having a limited range of MZ reach the transducer or the detector. So the positive rods, so these are alternating AC, causes ions to converge during positive arc and diverge during negative arc. If ions strike the rod during the negative arc, they are neutralized and removed by the vacuum, and striking your rod depends on the rate of movement through the rod, the mass to charge ratio, the frequency and magnitude of the AC signal. DC current affects the momentum of ions, so the momentum is directly related to the square root of mass, so more difficult to deflect heavy ions than lighter ions, and this prevents heavier atoms from striking the rods. And then, of course, we have to have a high pass mass filter. So the negative rods then, so in the absence of an alternating current, all positive ions are drawn to the rods, so they're therefore annihilated. This is offset for lighter ions by the alternating current. We have a low pass mass filter for this one. So the transmission for small masses is blocked. For ions to pass through the rods, the band of ions, they have to be significantly heavy to pass the positive rods, but they have to be significantly light to pass the negative rods. So one pair is attached to the positive side of a variable DC source, and the other is attached to the negative side of a variable DC source. So the adjusting the AC and DC moves the center of the band of ions through which pass the rods. So then time of flight mass analyzers, these are typically used in things like MALDI. So ions are generated by bombardment of the sample with a brief pulse of electrons. So ions are then accelerated by the electric field pulse of 10 to the 3, 10 to the 4 volts. So this is the same frequency as the ionization pulse, but it lags behind, so it comes sometime after. The accelerated particle then enters the field-free drift tube. Ions enter the tube with the same kinetic energy, and ion velocity varies inversely with mass. We then have lighter particles arriving at the detector before heavier particles, and the flight times are around 1 to 30 microseconds. And this requires fast electronics. Sometimes we have peak broadening due to the variability in ion energies at initial position, so the limits the resolution compared to magnets and quadrupole. It's less likely to be used in quadrupoles. However, it does have some advantages in that it has an unlimited mass range. It has rapid data acquisition. It's quite simple, it's quite rugged, and there's an ease of access to the ion source. They're just electrons. Electron multipliers then. So this detects positive ions, similar to the photomultiplier used in UV vis. So each dynode is held at successively higher voltage. So dinodes have a copper beryllium surface. So there's a burst of electrons emitted when struck with energetic ions or electrons. We have electron multiplies contain upwards of 20 dinodes, electron multipliers contain upwards of 20 dinodes. So there's a typical current gain of around 10 to the 7, so almost a million or more than a million. We have continuous diode electric multipliers. So this is glass that is heavily doped with lead, and the potential of 1.8 to 2 volts across the length of the transducer, and they're trumpet shaped to make sure that the ion actually will hit the surface near the entrance. Another type is the Faraday cup. So this is the one that was originally used in the first mass spectrometer. This is a hollow collector. It's open at one end and closed at the other. It's used to collect a beam of ions. So the incident ion strikes the dynode surface, which emits electrons, and induces a current which is amplified and recorded. And so it is surrounded by a cage which prevents the escape of reflected ions and ejected secondary electrons. So it's inclined with respect to the ion beam, and particles striking or leaving the electrode are reflected away from the entrance. It's connected to the ground potential through a large resistor. Ions striking the plate are neutralized by the flow of electrons from the resistor, and it causes a potential drop across the resistor. It's independent of the energy, mass, or chemical nature of the ion. It's inexpensive and simple mechanical electronic device. The disadvantages are the need for a high impedance amplifier. It limits the speed at which the spectrum can be scanned, and it's less sensitive than other electron multipliers. So what are some common interferences in atomic mass spectrum? So an ionic species in the plasma has the same mass charge value as the analyte. That's going to be a problem. If we have isobaric interference, so the two isotopes have the same, or two elements of the same mass, then sometimes they're going to overlap and be difficult to resolve. But this is easily predictable from abundance tables. If we have a polyatomic ion interference, this is more serious than isobaric. This is because polyatomic species form from interactions with the species in the plasma matrix or atmosphere, and so we're not quite sure where the interferences have come from, and so it can be hard to piece together exactly what is being what is sort of the cause of these interferences, but there are ways around it. We can correct with a blank, so we can see the different ions that might be produced just by the plasma itself. We can even add sacrificial things like ammonia. Spectroscopic interference, so we also have oxide and hydroxide species. So this is the most serious. So oxides and hydroxides of the analyte or the matrix solvent can form. We have AMO plus and MOH plus ions. And so the formation depends on the injector flow rate, the radio frequency power, the sampler Skinner spacing, the sample orifice size, plasma gas composition, oxygen elimination, and solvent removal efficiencies. So there's quite a few causes to this. You can also have matrix effects. We saw this was a big problem in MALDI. It's a general effect, the reduction in the analyte signal, because usually your matrix is more abundant than maybe your analyte, and so that causes some interference. So it's minimized by using more dilute solutions and altering sample introduction procedure, or by separating out offending species. And so we use the internal standard to correct the effect. So the effect of pesticide response to matrix effects. So here are different pesticides and the effect of different matrices on their relative response rates. And so we need to add a protectant to remove the matrix effect, because if we don't actually take into account the effect of our matrix, then it's possible that we will not know the actual quantity of our chosen analyte in our system. So Fourier transform MS, this removes the signal to noise ratios, or improves, the signal to noise ratios. It has greater speed, higher sensitivity and resolution because of the way that Fourier transform works. It means we can measure things simultaneously. So it requires an ion trap. Ions are circulated in well-defined orbits for extended periods. The ion cyclotron resonance, ICR, so ions in a magnetic field circulate in a plane perpendicular to the direction of the field. And so the angular frequency of this motion is going to be called the cyclotron frequency, which is given here as omega c is equal to v over r, which is equal to zeta EB over m, where zeta is the charge, E is the electronic charge, B is the magnetic field strength, and m is the mass. So the ion trapped in a magnetic field can absorb energy from an AC electric field. The frequency of the field must match the cyclotron frequency, and the absorbed energy increases the velocity of ion and radius without affecting omega c. So detection of ICR, ion circulating between plates induces a current between the plates. So we've got an image current, we've got non-destructive, and decays over a few seconds through collision. So the decay over time of the image current after applying an RF pulse is transformed from the time domain into a frequency domain, given here. And then ions of two different, so we can see here at the bottom, this is how it goes. So we've got radio frequency excitation, we've got the detected time domain image, then we Fourier transform it into a mass domain spectrum of all the different fragments. So ions of two different Q ratios are excited on resonance for the same amount of time with the same excitation voltage. Ion A has the lower MQ ratio and thus has a higher cyclotron frequency. Ion B has the higher MQ ratio and thus has a lower cyclotron frequency. Thank you for watching this overview of mass spectroscopy. I hope you enjoyed and learned something.